Okay, hello everybody. Thank you for coming. I'm Julien Guertot, known in the demo scene as Zavie of the group Ctrl-Alt-Test. I'm a programmer living in Tokyo, and I'm interested in rendering, and in a broader sense to anything that has to do with image, meaning drawing, painting, photography, you name it. And more specifically, I got more and more interested in light, as I think light really is a pillar of imaging, and by carefully using light, you can dramatically change the emotions conveyed by your image, being photo, cinema, or hopefully rendering too. So today, I'm going to talk about light. Light, according to Wikipedia, is electromagnetic radiation that is visible to the human eye and is responsible for the sense of sight. I like this description. It's pithy, and as obvious as it sounds, it highlights the fact that if you don't have light, you don't have sight. But light conveys much more information than this. Take a look at this painting, for example, from Gustave Caillebotte from late 19th century. It's presenting what appears to be some workers in, well, it seems to be some pretty usual flat in Paris, and they're working on the floor. And what I like in this painting is see how the painter used the reflections of light through the window to tell us a lot of things about the floor. See how the floor looks very smooth and glossy in the background, and how it looks very rough in the foreground, and how by just looking at this picture, you already can feel how it would be to touch the floor. And this only by using the reflection. So I think it would be great to have these kind of things in our rendering. I started documenting myself over the last few months because I wanted to get out of this situation, get past this situation where you just copy-paste a Phong shader you found on Google, you put it in your code. You don't completely understand it, and you have a big fight with it in this ambient, diffuse, and specular zoo, and you have a big fight tweaking these values, and at some point you just give up with... Is it still okay with the sound? Okay. And yeah, you have a big fight by tweaking values, and in the end, you end up with a result that is mediocre at best. And by documenting myself, what I found is, actually, it's not that difficult. There are a couple of ideas, a couple of insights. As soon as you have them, as soon as you understand them, you get to see the light in a very different way. So this is what I'm willing to share with you. Oh, sorry. This is what I'm willing to share with you today. Because unfortunately, as interesting as it is, rendering is just too much wide of a field to know it all and to document yourself on it all. So this is my attempt at saving you some time. And for me, it's an opportunity to try myself at talk. This talk is going to be divided in 3 parts. As the first part, we're going to remind a couple of the physics of light. Well, it's only a 1-hour talk, so we don't have much time to go into this, but just a few reminders to see what we're talking about. Then, as a second part, we're going to see a couple of usual models, very famous usual models, and try to understand what they really mean. And at the conclusion, we're going to try to connect those 2 dots, the physical nature of light, the models we have, and try to get toward a more physically based rendering. I'm still a beginner at this. I'm still learning this stuff, so there are probably a couple of mistakes along the way. If you know better, feel free to stop me and correct me. But anyway, let's go. So, physics of light. Light has a couple of properties that describe it. It has a direction. It goes from somewhere to somewhere else. It has an intensity. It can be bright, it can be dim. It has a speed, which is, well, it means it's not instantaneous. When it goes from one point to another point, it actually takes time to travel. It has a wavelength, which to us is perceived as color. And at last, it has a polarization, which we human beings cannot perceive, but a couple of species can actually recognize the polarization of light. Thinking about birds, for example. Some birds can actually recognize the polarization of light. The speed of light, 299,792,458 meters per second, which you could say is pretty damn fast. Actually, it's thought to be the ultimate speed you can ever reach in the universe. But anyway, it's kind of interesting that people realized the light had a speed, and they made a quite early experiment to try to measure that speed. And it's pretty interesting that as soon as, well, a couple of centuries ago, they already had quite a good idea of the order of magnitude of the speed of light by using devices made of like gears and mirrors and measuring over long distances. Well, they could make some measurements. It's pretty interesting. Light is thought to be a wave, an electromagnetic wave. And that means that the light is only a very thin part of the electromagnetic spectrum, along with microwave, along with radio waves, with X-rays, with gamma rays. The light has been thought for a long time to be made of particles, like small quantums of light, and the electromagnetic nature of light has been revealed first by Huygens, and the real breakthrough has been made by this guy in the middle, who is Augustin Fresnel, and who released a thesis to the Académie des Sciences, which is now considered to be one of the best pieces of work in science. I could talk about this guy during hours. It's pretty incredible if you ever had experiments on light at an institute or things like that, you know how difficult it is to set up an experiment to measure tiny things, and a tiny vibration and everything is broken. And this guy has been writing rules about light, has been predicting the behavior of light by doing experiments in the farm of his mother, by measuring the shape of light through honey drops, because he didn't have lenses. Pretty crazy stuff. Anyway, so it's an electromagnetic wave. An electromagnetic wave is defined by an electric field E and a magnetic field B. And I won't talk about this stuff, and I don't even remember what this means. I used to know this 10 years ago, but anyway. So it's described by the Maxwell equation, which describes the relation between E and B. Anyway, so you have this oscillation between E and B, and the light can oscillate, and the manner it oscillates around E and B makes a phase, and this is what defines the polarization, meaning that depending on the phase, you can have your light making a circle in one way or a circle in another way on anything in between. We're not going to talk about this, but just to remind that this stuff exists, and it's pretty interesting. Anyway, what is interesting for us is that electromagnetic wave is going to interact with matter, and this is described by the Fresnel equations, which are a direct consequences of Maxwell's equation. So, according to this website I found, the Fresnel equations give the ratio of the reflected and transmitted electric field amplitude to initial electric field for electromagnetic radiation incident on a dielectric. And if you understand this as first sight, you can just leave now. But anyway, what does it mean for us? It means that you have a material, you have a beam of light. This beam of light is going to interact with the matter. A part of it is going to be reflected, a part of it is going to be transmitted. And the Fresnel equations are going to tell us how much. And this is what is interesting to us. So the Fresnel equations tell us that the ratio between the reflected and the transmitted light is going to depend on some nature of the material and the angle of incidence. And basically for all materials, when the angle of its incidence tends to be tangent, it's going to be 1, like everything is reflected. Oh, sorry, it also depends on the wavelengths, and this is very important. But anyway, so what happens to the part of light that is reflected? This has been studied and written a long time ago already, and it's known as the law of reflection, which states that the angle of incidence equals the angle of reflection. So you have your beam of light incoming and beam of light reflected, and the angle are the same, which is, well, pretty handy because it's simple. This light, which bounces off, is what we refer to in light stuff as the specular component. So it's the reflection you see, for example, on the table, or whatever shiny you see, you always have a specular highlight. This is what we're referring to here. If the law of reflection is for a perfectly flat thing, like a perfect mirror, but in real life, like for example this table, it's not perfectly flat. So, for example, I'm seeing the reflection of the light over there, and it's pretty dim because the light is not perfectly flat. Then there is a part of light that is not reflected. It's going to be transmitted through the material. And what can happen to this light? Well, first, what can happen is just nothing. It's going through the material. It's not interacting with it. So think about water, for example. Think about air, think about glass. The light just goes through. What else can happen? Well, you have your photons, meaning the particle of the light, that are going through the material, and they can just bounce off the particles they meet. And because of the nature of the particle, because they are so numerous and so tiny, we cannot really predict what the direction of the photons are going to be. So at our scale, it's really random. And once a photon has bounced, it can bounce again and again and again. So what is happening at our scale is the light is kind of scattering through the material, and it's going to random directions. And if we get to a bigger scale, well, this light that has been scattering can just go off the material, and it seems to be re-emitted in all directions. It's re-emerging from the material in all directions. What else can happen? We have our particle, we have our photon incoming. What can happen is this photon is going to be absorbed by an electron, and the electron is going to jump to a higher state of energy, meaning heat. This is very specific to the light, because this behavior is going to change with the wavelength. And for example, with UV, it's going to have a different behavior, which is why the UV are considered so dangerous. And with gamma ray, the reaction is going to be even worse. And this, well, you know, gamma rays are pretty known for being not so nice rays. So in the case of light, the electron is going just to absorb the photon, which means you have a part of light that is getting absorbed, and while it's going through the material, the more and more light is getting absorbed, and because it depends on the wavelengths, some wavelengths are going to be absorbed and some are not. So the color of light is going to change while it's traveling through the material. So you can think of colored water, you can think of tinted glass, things like that. But now, if we combine this effect and the previous one, we can have our light that is scattering through the material, being absorbed and re-emerging. So what it means is the light that re-emerged from the material has a different color. And this color depends on the material because it's a material that, it's the nature of the material that defines which wavelengths are going to be absorbed or not. Depending on the material, the light can re-emerge very close or pretty far from the point it entered. And from our point of view, if the distance is very short enough so we cannot really see it, well, we just see the material reflecting the light. But if this distance is going to be significant, it seems the light is getting out from a distance. So this is what we refer to as subsurface scattering. This is what makes your hand shine through, well, for example, if you put a light through your hand and you see your skin behaving in a special way. This is the kind of stuff that happens. So, in summary, when light hits material, there are two things. There is a part that just bounces off immediately, and this is what we refer to as a specular component. And there is a part that goes through the material and re-emerges with possibly a different color, and this is what we call the diffuse component. And like I said, the Fresnel equations and the Fresnel coefficient tell us how much is going to be reflected and how much is going to re-emerge in a diffuse way. So those two parts are really physically different. And for example, when you look on the internet on explanation on what is diffuse light, sometimes you will see something like, yeah, when you have a material that is very smooth, very, very flat, everything is going to be reflected in a single direction, and this is specular. But if the material is rough, the reflections are in every direction, and this is diffuse. No, this is still specular. The diffuse is really physically different. And it's so different that Wikipedia has a very nice quote that I find very striking. It says, "A piece of highly polished white marble remains white. No amount of polishing will turn it into a mirror." And this makes completely obvious the fact that diffuse and specular are completely different. Like, you have a piece of marble, you can polish it as much as you want, it's not going to be a marble. It's not going to be, a mirror. But what happens on the other end? There are metals and semiconductors that have a peculiar behavior that all the transmitted light is immediately absorbed. It's not going to be re-emitted. And the consequence of this is metal do not have a diffuse component at all. The diffuse component of metal is pitch black. And this means the color of metals only comes from specular, because remember, the Fresnel coefficients depend on the wavelength, and this is what will change the color of metals. So we really have two physically different things, and it's so physically different that we can actually separate them by filtering, because if the specular component has a polarization which the diffuser has not. And by using what we call polarizing filter, we can filter out the specular component, the reflection, and that's something photographers are used to for a long time. You can buy a polarizing filter for your camera, and this allows you to get rid of the reflections through a window, for example. Or if you want to take underwater photo, you want to take photo of a river or something like that, you want to get rid of the reflection, you can use a polarizing reflection, or just reflections over the leaves or in the trees and things like that. And the funny thing is, if you can filter out specular, and you can then remove it from the original photo, like this guy did on his blog, to illustrate. And by doing this, he can take a photo and put the diffuse part and the specular part away, which is kind of interesting. Then it gives you an idea of what it really looks like, what should be the specular part and the diffuse part. Then, this was for the physics reminder. Let's go on to some shading models. So we said there are diffuse and specular. Well, for the diffuse, I won't go very far, just mentioning the Lambert one, and then we're going to see a couple of specular ones. So the Lambert is pretty old stuff. It's from photometria, well, 18th century. It states that the diffuse light that you get is function of the normal and the direction of the normal and the direction of the light. And it's pretty intuitive thing. And also, it has an interesting characteristic that when you think of a material, you have your lighting your material, and you think, yeah, the more grazing the angle is, the less light the material is going to receive. But this cancels out with the fact that the same happens in the viewing direction. So in the end, the material is going to reflect as much light in. Well, it's going to reflect the light in every direction. This is what the model states. This is what we call an ideal diffuse material. In reality, there is no such thing, I think. But anyway, it's considered to be close enough to be valid. So almost everyone in real time is using this. But if you think this model is not enough, you can use other models. A good example of a non-Lambertian material is the moon. Like if you take a photo of the moon and you make a rendering of a ball using Lambert, you're going to have a different result. Because you know, well, I think every one of us has seen the moon. And when you see the shadow of the moon, the contrast between the shadowed part of the moon and the lit part of the moon, there is no shades or whatsoever. It really comes white to black. And Lambert material don't have the, with a Lambert material you would have a shade, which you don't really have with the moon. But anyway, this model is pretty simple, it's intuitive, it's cheap, and it works pretty well. So this is an example of Lambert diffuse. Here you have diffuse only, with one light, and well, it seems to be reasonably correct to the eye. And here is what you get if you put two lights and some shadows. And then if you add texturing, you get this kind of result. So diffuse part, you already have detail, you already see some, well, I don't know if you see it clearly on the big screen, but you can already have some information on the materials here. So like I said, yeah, I already mentioned this slide. So like I said, in reality, materials are not ideal diffuse. Then to the specular part. So the most famous and pretty much oldest one is the Phong model. It is an empirical model, as in they made it up. It's simple and visually it's convincing, but it's not physically correct, and actually it's not even physically plausible. How does it work? Well, you have your material, you have your normal, you have your incoming ray of light. You know that for a perfectly flat surface, the law of reflection states that the light is going to be reflected toward R. But your material is not perfectly flat, and the direction of the viewer is V. So the question is, how much light is reflected in the direction V? Well, this model, what the model is taking some kind of a distance function between R and V. And the function it uses is a cosinus, well, here a scalar product, a dot product. And the dot product is going to be 1 if V and R are the same, and it's going to be 0 if they are orthogonal, and if it's going to be negative if they are toward opposite direction. And as soon as you have this, you narrow it with an exponent, so you can have a thinner peak in your function. And I underlined the equation to say that we're not interested in negative values. So we clump it. So this was the image with diffuse only, and this is what we get if we add some Phong reflection. On the left, we have a low exponent, like 1, I think. And on the right, we have a high exponent. I think it's ×2 for every tower. So I already find this image interesting. See how now, well, we started from this, which is, well, only a diffuse thing with a texture. And by just doing this, we already have on the left a part that looks like rough wood. And on the right, it already looks a bit glossy. So it's kind of interesting already. We can already do things with this. But there are a couple of problems. Like, remember that the dot product really is a cosinus. And remember that a cosinus, when it reaches 0, is pretty steep. So what is going to happen when the angle between V and R is more than 90 degrees? Well, the eye is very good at detecting contrast. And these discontinuities, we're going to see it. So if I put only the specular part, well, definitely on the left, we have a very strong contrast that is not very, very nice. And this is a drawback of this model, because we can have this situation. But, well, as soon as we have a high exponent enough, it's pretty good. So what else do we have? We have the Blinn-Phong model. which is an improvement on the Phong model. It still is empirical, but this time it takes reality into account somehow. But it's still not physically plausible. So what is this one? Well, this time we get rid of R and instead we introduce H, which is a halfway vector between L and V. And if you're like me, the first time you see this, you say, what? Like R, okay, I understand. L is supposed to be reflected toward R, but H, where does this come from? So the reflex here might be to go to Wikipedia for the help. And then you arrive on Wikipedia and you have this comparison image. And you're like, okay, I have such an object on my desk and certainly looks more like the Blinn-Phong one than the Phong one. Or maybe I just don't see the difference. Anyway, let's see a different image. Here you just have a plane, and the Blinn-Phong model is going to have this vertical line, and the Phong model is going to have a round shape. Okay, now I see there definitely is a difference, because here I don't see anything, but here definitely there is a difference. But which one is more correct? Let's have a break. I have a friend who is a photographer, and he has this funny project of going in every capital of Europe and taking photo of himself jumping in front of famous places. I definitely recommend you his Flickr page. But anyway, he took this photo in Prague of this bridge, Golden Charles of Prague, and sees those reflections on the water. Well, obviously the Blinn-Phong model has something correct. Like, yeah, we have this, we want those vertical lines, but why does this work? Well, see the water, we have some waves, and yeah, it's not perfectly flat, so there are parts that are reflecting the light toward us and parts that are not reflecting the part toward us. But which are the parts reflecting them? Well, those ones are the ones that respect the law of reflection. The one with normal is actually H. So this is where this H is coming from. We're considering the material to be made of microfacets, and the facets that have H as a normal are the one reflecting the normal. So in the end, what we're interested in is knowing how likely it is to have facets with H as a normal. So this time we're going to see to come up with a distance function between N and H, and again narrow it with an exponent. So this is the only difference, and this is how the Blinn-Phong model works. So what do we have as a difference? This was the Phong model, and this is the Blinn-Phong model. So in the end, there's not much difference. You can see that the light has definitely changed. It's more intense here, but none of them is physically correct. So in the end, you have to tweak the values. So it doesn't really make much sense. And beside the example I gave here, you don't see really much difference. But you can notice that we don't have this discontinuity problem anymore, because the case where the angle is more than 90 degrees just does not exist anymore, which comes handy. So this model is better for the discontinuity stuff, and it's better for grazing angles. So it's definitely better, and on nowadays hardware, it's pretty much the same speed. So far we've seen models that assume the light, the direction of light to be, well, sorry, the lighting to be direction independent. So you take like your object and you're turning around, and it doesn't really change anything, which means it has an isotropic behavior. But what happens if the reflection does depend on the direction? You can think of a CD, you can think of a vinyl, of brush material, of hair, things like that. This is what we call anisotropic behavior. There is a model I like that is very simple. So here is an example of definitely anisotropic behavior. So there is this model published in '98 by Wolfgang Enrich and Hans-Peter Siedel. which assumes a surface to be made of strands. Definitely makes sense when you see this kind of thing. It is pretty simple to implement, and the result is somewhat convincing. So I'm presenting here pretty quickly. Sorry about the screenshot. I didn't have to come up with one by myself here, so I shamelessly copy-pasted from the internet. So the idea is we suppose our material to be made of strands, and we're going to concentrate ourselves on one strand, and for one strand there is an infinity of normals around the strand. And instead of integrating our light equation over all this, we're going to consider only the most significant normal. And that normal is the one that is in the same plane as the light. So what do we have? We have the light, the direction of light. We have n, the most significant normal, and we have, well, the tangent that is describing the direction of the strand. And if we apply the Phong model is going to say that the specular is R times V. And, well, I'm not detailing it, but this paper shows that you can write it in terms of ln and t, and you have these equations. If you implement this one, you get this kind of result. So it's absolutely not physically correct. It's pretty strong assumption. So you see for low exponent, it's not really interesting. For high exponent, the image is not very good. But from a pretty short range of exponent, the image is kind of interesting and it's convincing, like feels like it's brushed metal. So I like this model. It's pretty simple. Then, and now we've seen those models that are not physically correct and sometimes completely careless about physics natures of light. So let's see what we can do. The problem is, so those models are not physically correct. They are experimental, it's completely ad hoc, it's, oh, I come up with this thing and it looks convincing. After all, like the visual result is more interesting, more important than correctness. We're not doing simulation here. But the problem is, some of these models are not even plausible. They don't even make sense at all. Well, the typical example is when you have a material that is reflecting more light than it received in the first place. But, well, we can still tweak values. Like, if you have your artist, he can just tweak values and get the result he wants. And he can get something convincing. But the problem is, those values are fudge factors, and they're completely disconnected from reality. And it's not really robust, because as soon as you have your scene that works, you change one parameter, you change your lighting, and it completely falls apart, because it's been tweaked against one lighting condition. If, on the other hand, we have some physically based rendering, well, we have a couple of interesting points. The implementation is going to make more sense. Like, you don't have a fudge value that doesn't make any sense. It's a physical value, so you can think about it. You can make a reasoning on it. So it's easier to implement, and it's easier to modify. It makes more sense. You know where, if you're going to come up with some ambient thing, if you're going to code some new thing, you know where to put it in your equation. You know if it's going to work or not. So you, in the end, you have less values to tweak that make more physical sense. And because it makes more physical sense, the result is more robust. It's going to be more robust against changing lighting conditions. And, well, as a coder, it means you have less needs you have less artistic needs. And in the end, what we're interested in, a better looking result. But how can we achieve that? A first step is to switch to an energy conserving model, because we saw that those models are completely senseless. And so there is a law of conservation of energy. You don't want your material to reflect more light than is received. And you want your equation to have such a behavior. So the solution to this would be to have a real equation, but you can just fix your ad hoc model by integrating over the hemisphere and make sure that the result you get is not higher than 1. And if it is, then you get a normalization factor that you apply to your equation. And that way you're sure that your lighting equation is not going to reflect more light than it received. So if we apply this to the Phong model, so the original equation was v dot r power n. And if you integrate this, you get as a result that the normalization factor is n plus 1 on 2p. So if you change your equation, well, you get this one. You may notice that the p has somehow disappeared. Well, this actually, it's kind of easier to remove the p because it cancels itself against the light stuff. And anyway, it's a constant factor, so you just remove it. Like you know you might eventually have a by-3 factor. But anyway, so this is what you get, and you have this normalization factor, which is function of n. And if you apply it, so this was the original Phong screenshot. And on the left, it's pretty interesting that you have this rough look. But on the right, the reflections are pretty dim. And it makes sense because we had something we elevated to a power, and the function got narrower and narrower. And that makes less energy. But if we normalize, then we get this kind of results. Well, maybe it's too bright, but it certainly looks more interesting than this. Like now, we really have on the left rough wood. On the right, we have like coated wood or something like that. So when I have this, I'm already happy with my image. I'm like, oh, it's much better. I'm happy with that. Now let's go to the Blinn-Phong. Blinn-Phong is a bit more tedious because the normalization factor is it's a bit heavy, and we don't really want to have this on our hardware. But the fact is, you can use an approximation by using bounds. Like, I've seen 2 approximations, like the 2 I've wrote, which are lower bound and upper bound, it seems. So you can just pick up one of them and apply it to your equation. And then you go from this, which was the original Blinn-Phong, to this, which looks certainly much better. You may notice that on the left, we lost some light. It was much brighter on the left. So I suppose this is due to the fact that it's an approximation. But anyway, so we have this, and yeah, we're pretty happy with it too. So now, to finish, I'm just going to say a few words on the microfacet BRDF. It's bidirectional reflectance distribution function, and I certainly don't have time to talk about this. It would take 1 talk or more for this alone. The usual form of microfacet BRDF is F times G times D over this. So what are those F, G, and D? Well, F is a Fresnel reflectance. So far, in the image before, I used a constant factor for the specular component. And that was yet another fudge factor. I'm like, OK, 0.5 is too high, 1 is definitely too high. So I just put 0.2, and it's completely senseless. But we can use the Fresnel reflectance, because Fresnel is telling us how much light is being reflected, and so we can just put it into a function. Now, the D function, normal distribution, is what we just seen, like Phong model, Blinn model, are implementations of the D function. And then we have another function that I didn't mention at all, which is the G function, the geometry factor. It's the one that tells us how much light is going to be intercepted by the material itself. Because if it's rough, like the cast light is going to self-shadow and things like that. So far, we've made the assumption that G over 4NL NV is just 1, which is kind of reasonable too. So the interesting thing is you have this equation, and you can just play with it, and it's like Lego. You can just change G and D as you want, as you see fit. Now, so this equation is sort of the Cook-Torrance, and it's pretty expensive. There is a paper of Schlick that takes the crook torrents model and tries to get approximation of all those parts to get a cheap BRDF. Usually the Schlick's approximation refers to the F part. In his paper, he's being approximating all those functions, but the F part is the most famous. So the F part, the Fresnel part is kind of expensive, but here is his approximation, which is much faster to compute and much easier. Problem of this equation is that it assumes the imaginary part, because the Fresnel factor is a complex number. And by doing this, he's assuming that the imaginary part is null. And it's true for many materials, but it's absolutely not true for metals. So this means his approximation is not going to work at all for metals. But if you want to use it for metals, there are some papers that improve over his approximation and try to make it better. So if we use this, so this was the Blinn-Phong specular, and like I said, with some factor I come up with to make it look like I want it. And this is what I get if I